All right, hi. So without further ado, let's just continue where we left off. Last video I actually talked about how to, well, basically possibly how to solve the Newton's law of cooling problem using this, some of these derivations here, just described using the type system. Okay, so what we have is T plus delta T solid. Okay, the next time step, the temperature at the next time step. Okay. Let me see. Where's OBS? Yeah, there you go. Okay, so the temperature at the next time step is determined by all these factors right here, and we want to code that into Rust. Okay. So so far we have gone through quite a fair bit just to learn how to put a new function in another file. And just to put a new function in another file, we have to go through several steps. Okay, we have to tell from this file tell the file that, hey, this file exists, this other file exists called Newton's law of cooling, and then we have to tell them, okay, we want to use this function implicit Euler method within the Newton's law of cooling file. Okay, that's how things are done. Okay, so next, all right, we have all of these, right? We want mass, CP, delta T, HA, T surroundings, MCP, delta T, T solid over delta T. Okay, so right, well, what do we do? Okay, so let's start scripting all of this. So let's script the MCP. Okay, so remember how to declare variables, right? How to declare variables. To declare variables, we use the let keyword. Okay, so I'm going to let mass equals to maybe something like 2.0. Okay, mass equals to 2.0. Let CP equals to 3.0. Okay, so M and CP are coded. Okay, H and A, let's code H and A. And let heat transfer coefficient equals to 20.0. Okay, heat transfer coefficient equals 20.0. Let surface area equals to 5. Okay, so we have HA already done, MCP delta T already done. So HA and T surroundings. So we will need T surroundings. Let temp surrounding. Okay, maybe let's put 25 degrees C, just like we did before. Okay, MCP. Okay, we need a T solid over delta T. So we need delta T, which is the time step, equals to 0.1. Let well, what else? T surrounding delta T and T solid, temp solid, last time step. Okay, so maybe let's put this at 400. Okay, of course, right, there are a number of problems with this. So yeah, there are a number of problems with this. First thing first, this thing is not dimensioned, right? If I say mass is 2 what? 2 kg, 2 grams, 2 pounds. CP is also not dimensioned. Okay, so it's very easy to make mistakes. So let's say you do something like okay, we have two things here to calculate, right? There's a denominator and there's a numerator. Okay, so so this denominator is MCP over delta T. So denom term 1 equals to mass, okay, so times is the asterisk times CP divided by delta T, right? Or you just use time step. Okay, if you do it right, it's fine. If you do it right, it's fine. Let's say you actually make a careless mistake. and you actually type mcp minus time step. Okay, you will still calculate denominator term 1, but if you don't realize this mistake early enough, you will run into bugs later. You run into bugs later, and then you will find yourself in trouble. So there must be ways of actually making sure this thing works. So this is actually one problem. Okay, so I'm going to do this. I'm going to add a comment here which says solve dimensions. Okay, solve dimensions first, or solve dimensions. I'll do this in a later video. Okay, solve dimensions. Now this one I'll do it in a later video, but I just want to put a mark down there saying, hey, this is a problem. There is a way to solve it. I'm not going to introduce it that early. Second thing, well, you notice that the solid temperature at the last time step, this is something that will always change, right? You see when the ball actually so-called is starting to cool down, the temperature of the so-called ball is constantly changing with time. And because that is the case, you will need to actually constantly tell, okay, in this equation, this T solid at the last time step, it will continuously change. So you must have a way of telling T solid at the last time step to continuously change. Okay, how do you do that? Okay, so there are a number of things we can do. All right, first thing first, well, instead of defining what the solid time step is within the function, okay, instead of doing telling, okay, what is the solid temperature the last time step within this function, what I can do is I will have this as a function input. Okay, I will have this as a function input. Okay, maybe I'm jumping too far ahead. All right, so before I do that, maybe I'll do even simpler. Before I do a function inputs, I'll do everything within this function first. Okay, so this is a solid temperature of the solid at the last time step. Okay, maybe what I'll do is I'll say this is the initial temperature. Now that will make it always hold true, right? That will make it always hold true. Okay, what I'll do instead is I will start entering a loop, because what this solver needs to do to find out the temperature profile over time is that you start out with an initial temperature, and then you calculate the temperature at the next time step, and then you'll say, okay, let's say T equals to 0, right? At T equals to 0, the solid temperature is 400. You calculate the solid temperature at T equals to 1. Okay, so solid temperature at T equals to 1 will be calculated. And then if you want the solid temperature at T equals to 2, you will substitute delta T equals to 1 second. The solid temperature at T equals to 1 will be the solid temperature at the last time step. And the solid temperature at the next time step, T equals to 2, will be calculated like so. So this is what we'll do. You'll need actually a for loop to calculate this from, let's say, T equals to 1 to say T equals to something like 400. Okay, so we can do that in a for loop. Okay, for I, so this is how you actually code for loops, right? For I in, okay, you start from 0 and you use a dot dot. So you go from 0 to some big number. Okay, how many time steps do you want to calculate? Maybe let's do 100 time steps. Okay, for I equals 0 in 1 to 100. So this is how you actually do a for loop. Okay, this is how you actually do a for loop. If you're not sure, Russ will tell you what to do, hopefully. Let's say I equals to 0 to 25. You'll say it's wrong. Okay, okay. Well, I guess I overestimated this compiler. I thought it will tell you what to do. Apparently now, no. Okay, but this is what you need to do. 0 dot dot 100. So what this is doing is that you will have a variable I. The loop variable is I. Okay, and it will cycle from I equals to 0 all the way to I equals to 100, or more correctly, I equals to 99. So what you can do, right, with this for loop is to actually print the value of I. I'm going to print the value of I right now. Print the value of I using the debug function, or debug macro, excuse me. So you can see that I equals, it will start from 0 and you'll go all the way up to 99. Now, what is this ampersand sign here? Okay, that's another concept that I will need to introduce. It's called references and borrowing. Okay, but it's a little bit too early for that. I'll just write the note here called introduce references and borrowing later. Okay, we'll come to this later. Okay, we'll come to this later because technically you don't need to have this borrowing to print the value of I. What you can do is use the print line macro. Print line I. Okay, print line I, there will be some error. Okay, Rust will tell you what to do, or Cargo will tell you what to do. Just copy and paste here. This curly braces right here. Okay, so I is actually going from 0 all the way to 99. Okay, great. So we've ascertained that for this for loop, you actually run this loop 100 times. So we're actually running this calculation for 100 time steps. Okay, that's a start. Okay, that's a start. Not perfect, but that's a start. All right. So what do we need to do within each time step? Okay, we need solid, and we need the solid temperature at the present time step and the solid temperature at the last time step. Okay, so I'm going to declare two new variables. Let solid temperature current time step equals to 400. Okay, let solid temperature last, or rather current, next time step equals to, okay, something equals to what? Maybe 400? Okay, I don't know. Okay, I'm just going to use placeholder values first because this is simple. Because there's a better way of doing this, but I'm not going to go through that for now. Let's keep things simple. Okay, so what I want to do at every time step is to calculate this denominator term. So MCP over delta t. So let's do the denominator term 1. I'll put it here. Okay, MCP over delta t. The next one is what? HA. Okay, HA. So H, heat transfer coefficient, times surface area. Okay, so this is denominator term 2, excuse me, denominator term 2. Okay, and now I'm going to say let denominator equals to denom term 1 plus denom term 2. Okay, what have I just done? MCP over delta t plus HA, right? MCP over delta t plus HA. So that's the whole denominator. So now let's do the same for the numerator. HA t surroundings. Okay, let's see. Let HAT surroundings, right? HAT surroundings. So this is numerator term 1 equals to heat transfer coefficient times surface area times T surroundings, right? Temperature of the surrounding. Okay, that's 1. And then what's next? MCP T solid over delta T. Okay, let numerator term 2 equals to, so what do you need to do? Solid temperature at the last time step, or current time step rather, solid temperature at current times, or MCP first. Let's do MCP first. Mass times CP times solid temperature at the current time step divided by delta T, or the time step itself. Okay, MCP T solid over delta T, right? MCP T solid over delta T. Okay, so the numerator is there. Let numerator equals to numerator term 1 plus numerator term 2. Okay, so you have these two numerator, and the numerator term in this big bracket, the denominator term in this smaller bracket. So T solid is equals the numerator divided by the denominator. Okay, that solid temperature at next time step equals to equals to numerator divided by denominator. And you're going to run into a problem right now. Or rather, pardon. You will run into a problem if I do this. Okay, I take the let keyword out. What am I doing? So what I'm doing here, if I don't use the let keyword, the let keyword is to introduce a new variable. So I actually said before, solid temperature at next time step is equals to 400. When I use this let keyword, it will actually override this value right here. It will override. Okay, you're actually making a new variable of exactly the same name. So that means this whole variable here will be deleted. Okay, now let's say I don't want to do that. I just want to change the value of this variable called solid temperature at next time step. All right. So the solid temperature at the next time step. Now, if I want to change the value, I have to take out this let keyword. Okay, and what's it say? First assignment to solid temperature time step is here. Consider making this binding mutable. Okay, so Rust, okay, the thing about Rust is by default, you cannot change the values of variables once you initiate them. Okay, if you want to make the values changeable, or what we like to call mutable, then you have to introduce the mute keyword. This will actually tell you that these variables are something you can actually change. So the mute keyword here, very important. Okay, this is what the compiler is teaching, you. Oops, it should be this one. Okay, so, right. So this is half done. This is not fully done yet, but let's print the value of the temperature at the next time step. And let's see, it should be lower than 400 if I'm not wrong. Okay, I'll need to put the bang sign or exclamation mark. Okay. Right, and what's the temperature here? Temperature here is 165.625, so it is indeed lower than 400. Probably a little bit too low. Maybe I should actually increase the heat capacity, because this is a little bit low, right? It's a little bit low. Okay, I'm going to increase it by 1,000 times. And you can see that the temperature is just slightly decreased. Now this is something a little bit more realistic. But yeah, that's the thing about units, right? Case in point. In case you wanted 3 kilojoules per gram per degree C, okay, and you forgot to, sort of include it in your code, then you're gonna end up with these erroneous values that, okay, let me repeat myself. Okay, if let's say the units are, the units of these variables here you don't specify, you might actually get the wrong values, because the ball was at 400 degrees C at the first time step, and 0.1 seconds later it cools down to 165.625. Now, if you actually don't dimension your variables, you don't tell it whether it's kg or whether it's joules or kilojoules, you're going to run into this problem. And you don't know where you don't know what units those numbers are in. It's going to cause a lot of problems. So there are workarounds around that, but for now, there are ways to deal with that, but for now, I'll just let CP equals to this much, 3000. What units? Don't know. We'll deal with that later. Okay, so we actually see that temperature has slightly decreased. This is correct. We have actually calculated the temperature of the solid at the next time step is actually cooling down a little bit, similar to what Newton's law of cooling, it makes us, we should expect this kind of behavior, right? We should expect this kind of behavior from Newton's law of cooling, after all. So these are still reasonable values. I mean, at least none of them are like negative or anything, but yeah. Yeah, we'll deal with the units later. Yes, so yeah, we have calculated the temperature of the solid at the next time step. So how do we obtain the temperature of the solid over time? We should actually see a steadily decaying curve. Right. If you actually solve this ODE, this first order ODE, if you solve it analytically, you are going to see exponential functions, exponential decay functions, right? What you will actually do is you will say you do separation of variables. Yeah, you do separation of variables. The dt goes to the right side, the t solid minus t surrounding goes to the left side, and you'll end up with a logarithm of natural log, and you'll go exponential. It's an exponential decay curve. All right, so that's what you will expect. You should expect exponential decay curve, right? So how are you supposed to do that, right? I actually need to say, okay, let's say at let me go and draw. Okay. Okay, let's do it here. So this is called the time stepping. Okay, we need to do time stepping. Right, so what happens? At t equals to 0, this is going to happen. Okay, t equals to 0. So what's the t plus delta t? Let's put delta t equals to what we did just now. Delta t equals to 0.1 seconds, for example. Yeah, I'm going to actually put units now, at least when I write things. So t plus delta t will be 0.1 seconds. And t here will be 0 seconds, right? Oops, wrong one. 0.0 seconds. Let's put it like that. This is actually how you calculate. Okay, so at the end of this, you should be able to get the t solid at 0.1 seconds. But you're gonna have a to continue, you actually need to compute the temperature at the next time step. Okay, so let's say at t equals to 1, right? Now you need to go to t equals to 1 or 0.1. Okay, the relevant thing you actually calculate is this. As follows: the temperature at the next time step, which is 0.2 seconds, is equals to all of this, and then you times the t solid at 0.1. You have this t solid at 0.1 seconds right here. Okay, so how am I supposed to do this? Okay, the temperature at the last time step must be changed to this value, t 0.1 seconds. Okay, and the temperature at the next time step, okay, the current temperature must be updated to this t 0.1 second on solid, t solid at 0.1 seconds, and the temperature at the next time step will be, you put a new value into it. Okay, so to do that in Rust, you do basically the same thing, right? After you print, I will say solid temperature at the current time step equals to solid temperature at the next time step. And that's it. Okay, you will complain that it's not mutable, so you have to make it mutable. And this one will be the initial value. Okay, so now you will see that actually the algorithm works. Okay, let me change the thing from last time step initial to initial. Okay, we see that after 100 time steps, it actually cools down to maybe 342, right? So we see, let me get rid of this I. Okay, the comment for Rust is very similar to C. You use double forward slashes. Okay, double forward slashes. Okay, so here's the temperature. It starts at 400, 399.37, 398, 398, 397, 396, so on and so forth. All right. So at least physically speaking, this code does seem to do its job. All right. This code does seem to do its job. It's a very crude code, but we are getting somewhere. Okay, we're getting somewhere. All right, but we have sort of done an implicit method thing in Rust. I've shown you about for loops. Okay, for loops. All right, I talked about for loops, and I've talked about mutability, things like this, mute, and of course we want to put bookmarks and check marks for references. We'll talk about those later, and then we'll talk about dimensions as well, but we'll talk about them later. We want to sort of improve this code to make it a little bit more polished, a little bit more, well, more general, right? So that if we have solids of various, or solids or liquids of various kinds, various heat capacities, various shapes, we will still be able to calculate this Newton's law of cooling, right? Or lump heat capacitance. Yeah. So I think that's all for now. I'll see you guys next time.